Alright, DraftScience video. Yay. Okay, a response video to a text comment. And it's kind of a complex subject. So, um, I mean, it gets a little bit complicated. It's going to be kind of technical stuff. So, not fundamental to the theory, but sort of interesting. Anyway, so we're on this induction idea that this gravity sort of has to be induced. I mean, there's a process by which two gravitational bodies move into each other, and in that process, gravity grows through the process. And that also there has to be an accounting for the speed of light and how this shadowing effect could be possible when the shadow takes a while to be cast. And so that's an important fact. And so that's the argument is the rotation of the objects in the gravitational mix, their spin, is what's spinning the gravity in a direction and putting an angle on it. So it's just like this whole directional idea of if arrows are going through a medium that's moving and they're being, they're going to interact with that medium in the sense that this medium is made out of them. Its arrows going the other way, and so there's going to be an exchange of directional information. It makes sense that the net direction is going to have an angle to it. That's the shadow is going to be bent or diffracted, consistent with the spin. So anyway, this guy writes, so it's a little bit complicated. If equal pressure passes onto the sun and then exited, then there would be a field of effect, not necessarily a shadow. Well, exactly. The shadow doesn't show up until it's induced by the object coming into the influence of the other object. So one's acceleration creates the shadow. So once the object shows up, it initiates an acceleration, and the acceleration is essentially an absorption of an arrow coming through it. So if I move up, there has to be an arrow that pushed me up, so to speak, and I consumed that pushing up arrow to go up, and therefore there's less pushing up arrows ahead of me because I consumed a couple to go up. So when the body moves into the gravitational field, it induces acceleration. That acceleration absorbs arrows. Then there's a shadow cast on the sun. Then the sun, from that shadow, an area of the sun will move now, will accelerate because it's getting less arrows going one way, so more arrows come the other way, and there's the piece of the sun moves. And when the sun accelerates, it does the same thing, creating a shadow on the other thing, and it's just, that's the induction. From only one vector, so the sun shooting out a gravity ray leading to the planet isn't necessary. Well, of course it's necessary in the sense that you have to induce the gravity. It's all because there's a conservation of direction. Okay, so it's the conservation rule dictates that you have to, something has to go, it has to be used somehow. You have to use a directional arrow for it to be missing, or for a shadow to be created. The orbits are elliptical and not circular. Yeah, that's relevant, but not terribly relevant when you consider that the orbits are so close to circular that it doesn't matter. The ellipses are so not very elliptical for most of the planets that it's not really important, but I will explain it. So the spin of the sun couldn't lead to the planets with a line or ray of gravity accurately. Well, they can because of that whole equal distance swept kind of rule. So it will draw an elliptical orbit. So what you can understand is that for equal distances and speed, so this would be, the argument would be that obviously things have to speed up here, so things are moving. I mean, they have to go fast here because they have to cover a lot of ground to create this pie chart that would equal this one. They're going slow here. All right, they're gaining speed this way, and they're losing speed this way. Well, I guess it was just minus sign here, plus sign. So as they go around, this is their slowest point, then they start to move towards the gravity, which means they're accelerating in the same direction of their velocity. So their velocity increases to a maximum somewhere in here, where they start to leave the gravitational field, and then I guess that maximum would be here. And then this is where they're starting to go further and further away from. There's less and less. The gravity is in the opposite pull. I mean, the gravity is actually pulling against their velocity, stealing some of it, and then it's gaining velocity going around. So the point would be is that the time argument is the speed of light. This is where it gets complicated, right? Because you got three things to measure. You got the velocity, of the object. Then you got the speed of light, the distance it's traveling. So it has to make this round trip. And then the round trip on this side is obviously going to be shorter. So that's a difference in time. And then you have the spin angle, which is the rotation of this object. So the theory is that when it's going slower, the length of the speed of light is longer. So it takes longer for the signal to go from one to the other. But it's moving slower, so that means it doesn't get too far ahead. Here, where it's moving faster, the speed of light is quicker, so it will the gravity will make the round trip at a smaller portion in the cycle, by this drawing like 1 to 3 kind of a ratio. So for every 3, for every 1 time gravity makes the round trip here, the round trip will be made 3 times on this side by this ratio. But you can sort of get the idea that what's compensating for it is when the thing is moving faster, it's further away, so it's a longer distance, when the thing is moving slower. Sorry, when the velocity is the slowest, the thing is the furthest away, and the angle is the longest. So, I mean, it's like obviously the further away something is, the bigger this angle gets. And the smaller the distance, the shorter the angle gets. So when it's going faster, it's this shorter angle, you have to remember, is where the gravity shadow will be. So it's increasing proportional. So it's you can just think of it as that it's proportionally reciprocal. So as the speed slows down, the angle creates a bigger stretch, but there's more time because the speed of light is slower. And then when the speed of light is quicker, the amount of distance moved is more because the velocity is higher. But obviously there's more, it's quicker, so there's less angle. It's the same angle, but I mean it's shorter because the distance is shorter, so there's less distance to have to be traveled. I think you can understand that, right? Well, if you know what the hell if you know to write this comment, then you knew what I just said. The orbits are elliptical and not circular. See, technically they could be circular. I think if an object comes into the gravity at just the right angle, at just the right velocity, it could hit a perfect orbit. But the odds of a perfect orbit are not very high. So the spin of the sun couldn't lead to planets with a line or ray of gravity accurately. Again, it's not a ray of gravity. That's kind of the wrong way to look at it. But obviously it's a packet of gravity. Some orbits are extremely eccentric, such as Pluto, and even more for comets. Yeah, and that's, like I said, but they're really not hard ellipses in the sense that they're not as dramatic as even this. They're close to it. Pluto's kind of close to that. But like I said, it compensates because of like I said, as the object's moving faster, it's closer, which means the speed of light. The distance is shorter, which means the gravity doesn't have to compensate for as much because it's a shorter distance. So the fact that it's moving faster won't matter because the gravity's moving faster also in proportion to the distance. So it works out okay. Orbital mechanics is well understood even without knowing exactly how gravity works on the atomic scale. Well, I don't even think they understand that this is an atomic function. So right there, you're saying the mechanics are well understood, when I think most scientists still have this notion that gravity is affecting matter, and they're not realizing that gravity is really affecting subatomic particles. If your shadow hypothesis For your shadow hypothesis to function, then the force which causes the effect of gravity would have to come from outside the universe. That's a preposterous nonsense. It's a big bang. It's like any kind of pressure gradient. If you have a nuclear bomb, you have pressure build up because the pressure can't get released because the surface of whatever exploded doesn't particulate the same as the interior explodes more into a finer grain than the exterior, and the exterior blocks the stuff on the inside, so the stuff on the inside ends up bouncing off the shell of the other stuff, and that's where you end up with a pressure gradient. So it's just like a bang, big bang. There's pressure waves, and we're in a pressure wave, which means everything is moving out and back. Anyway, and would need to penetrate it from all sides equally. Yeah, well, exactly, just like the background radiation, the background microwave radiation is doing that right now. So we already understand that there can be thermal, whatever you want to call them, forces, the residue that creates an equal pressure. There would be movement of all matter in one direction more than others. Why would it be more than one direction? Again, it's an equal pressure. It's pressure. You can't have pressure without it being equal. It wouldn't be pressure if it had an escape hatch somewhere. Expansion in all directions without a center is what has been observed. Well, they're doubting some of those observations, but it's not really observations, right? They're calculations. So calculation is a little different than observation. And I think that's all I need to say about that. So anyway, I think I've addressed your major point. The rest of your point I don't think is relevant. The argument is that the pressure exists and gravity is a manifestation of it, and it doesn't really matter where it comes from, but I'm just saying you can logically intuit it from the Big Bang. If the Big Bang is true, there's every reason to believe that pressure gradients of gravity would be created. There would be densities of energy, and it would also explain why at the end of the universe, from observations, it appears like everything is producing a tremendous amount of energy as if everything was falling apart. And that would theoretically be exactly what is happening, because everything is in fact falling apart as it leaves the heavy gravity here. It does end up gaining tremendous velocity because the exterior of the pressure gradient, everything's one way, and it starts accelerating in that one direction very fast, and as it accelerates faster and faster, the matter itself breaks down and it releases all of its photons. Alright, so that's probably enough. Unrelated to the video, but really not. Okay, so I'm trying to get what you talk about in these videos, some of it right, but far from all. Can you or someone recommend some online courses or text or lectures to get the basics on the subject? Well, that's the whole problem. It really goes to the core of all the fundamental premises in physics. Einstein was wrong about relative velocity. Einstein was wrong about lensing. Einstein was just wrong. E equals mc squared. It's really just matter is energy. It's just energy trapped, and all energy is just these directional arrows, and all the energy is the same energy that's ever existed. It's just trapped in condensations of direction, balances of, filters of direction. A circle. Circle is a kind of a complex thing. Even though it's simple, it's complex in the sense that it has no direction, correct? It's equally moving in all directions and going nowhere. So it's energy that has no direction. And once you release the energy, give it back its directionality, then we call it energy. So it's a school of fish. A school of fish in one place swirling around each other uses just as much energy as a school of fish moving 30 miles an hour in a direction. There's no difference in how much energy they're using. There's no difference in how much plankton they're hitting. It's all exactly the same. It doesn't look the same, but it is the same in terms of the energy. Anyway, all right, so I just wanted to take care of that comment. This is kind of a, this is new. This part of the argument that accounts for the speed of light and the spin idea, and also the induction thing, that you have to induce the gravitational shadow. The shadow doesn't exist until the object shows up to induce the shadow. Yeah. Alright. So I'm going to try to write this shit up and submit it for whatever peer review I can get, but I would like to just buy peer review. If I can just buy it from somebody. I mean, really, some big name physicist, some douchebag, whatever, is Neil deGrasse Tyson. How much do I have to pay you an hour? $500 an hour? Come on. What's it take to have you comment? Yeah. What's it take to get some talking head, one of these physicists that have a voice, to attempt to embarrass them? Because that's it. I mean, if they trash it, I'll just embarrass them. So that's my win, and I get what I need, which is the peer review. So apparently, you don't have to be peer reviewed successfully. You just have to be peer reviewed. Apparently. Anyway, so till next time. Such.